look at some solutions. I have some things prepared, but I'm interested to see what you come up with. And so we'll see what we can collect for the first one. I didn't see anyone who actually graphed the quadratic. If you graph it, then where it crosses the x-axis, those are your two roots, your two solutions, -3 and 7.
Which is more time consuming.
And nobody brought their graph.
Right, okay.
But this is, I think, for students, this is a classic way to solve it, because they know the connection between the roots of an equation and the x-intercepts of the graph. It's a parabola, so some important things are the axis of symmetry is right here in between the two roots. That's -5. That shows up in a lot of solutions. And the two solutions are 2 in either direction, starting at 5. So no one had that way. Here's another way. I saw some people factoring it. Who factored it? And Paul, you had a really nice method. I saw this years ago. But you draw an X, and then you take the numbers 10 and 21. Where do you put them?
I don't know if there's a specific way that someone just showed me the other day. It's a good visual if the kid needs it. And I put the 10 on the top and the 21 on the bottom, and then just went what two factors multiplied and added give you the 10 on the top and what two multiplied give you the 21 on the bottom. Just a visual organizer for kids as well.
I think you can start teaching quadratics by putting the numbers here first, and then asking them what's their sum and what's their product. And here's the reverse problem. Here's the sum, here's the product. What are the two numbers? That's a nice way to approach it. But really, that's all we're doing. If it factors nicely, then we're looking for the two numbers so that there's the product and there's the sum. And once we find those two numbers, we factor it. And if we have 0 on the left side, on the right-hand side, you know that if you multiply two numbers and you get 0, then one of the factors has to be 0. And so this is a reduction already. We started with a quadratic equation, but using that property of 0, that multiplicative property, it reduces to two linear equations. Either x plus 3 is 0, or x plus 7 is 0. So it's a reduction to two simpler equations that we can solve, and we'll get to two solutions. I saw a lot of people use the quadratic formula right up here, and notice that this gives the -5 plus or minus the 2. So right there, it's the axis of symmetry of the parabola is hiding right there, right here, -b/2a in the quadratic formula, which is something, if we teach parabolas, we teach that axis of symmetry, but we don't always show the connection to the quadratic formula. Who completed the square? You guys got that? And Lorna? So here's how I did it. Is this how you do it? You take a constant, move it over to the other side, and then you do the square. And you mentioned that you had a geometric way to do this.
A geometric way to complete a square?
To complete the square. So I actually changed this. I had a -10x to begin with, but I changed it because...
I mean, you know the picture, or?
Can you come up and show us? Plenty of space up here.
Yeah, so I mean, if you have x squared plus bx, then what you really have here is you have the square side by x.
Let's use 10x instead of bx.
Okay, sorry, right. Okay, so then I think of this 10x as actually being 2 5x. 2 5x's. And so again, you see you have this b over 2a. So it's 5 and 2. And so if I put my 5's here, then you see that this has area x squared. These guys both have area 5x. here you see that they said there we have 25. And so the 25 term that you're adding on is actually coming from literally completing a square. And so this is the way that Al-Khwarizmi, I think is how you pronounce it. Actually, if you go back historically and look at the Arabic geometric algebraists, all of their writings, they didn't have any variables. All of their writings were always with respect to an unknown quantity, and then they would draw pictures like this, like that, geometric number.
Does anybody teach with algebra tiles?
No, I don't know.
Because this is something that's
This makes sense.
do with algebra tiles.
Yeah, well,
I originally had this problem set up with negative 10x, but then you have to subtract 5, and that would be a more complicated picture. I wanted to make this as simple as possible.
well, and actually, if you did subtract, the way that picture looks is that then you subtracted out the upper right box twice. So you have to add it back in.
Okay.
Right, because then you have an x by x box, and if you subtract off the x by minus 5x and the x by minus 5x, the upper corner's been subtracted twice.
So your 2 outer rectangular boxes would be within it.
Right, within it, that's
Yes.
right.
Which would leave that other one that then is a subtraction.
And it's subtracted once for each rectangle.
And if you have algebra tiles, to make it negative, you turn it over, and so you have to turn it over twice, and it would come out positive again. I don't have algebra
Does that
tiles.
make sense?
Yeah. I teach mostly algebra, very little geometry, and so I love to see geometric application.
So here again, notice that we've completed the square. So we have a perfect square on the left side, and we can take a square root of 4. We're asking what number when squared gives the answer of 4, and there's 2 answers. There's the square root of 4, and there's the negative square root of 4.
Right.
So x plus 5 is either the square root or the negative square root of 4. And x is, to get x, you just subtract 5 off. We have this negative 5, and then plus or minus to get the actual 2 roots. But here's the axis of symmetry, and the shift to get to the roots. Do you students have problems with there being 2 square roots? Because that's
Initially, because they just don't get it early enough.
Yeah.
But the question here is, what number when squared gives 4?
So
And
you
there's
have to
2
show it.
answers.
You have to show it.
But as we move on, we want to use the square root function. If it's a function, then there's only 1 square root, and by default we use the positive one. Until we get to complex numbers, and then there's no positive. Ben, you said that we have to depress the quadratic. Someone was asking me, why is this the state of the mood of the quadratic? Why is it depressed?
I don't actually know why that language was used, but that is definitely, that was the terminology back.
But what we want to do,
Do you know why?
I don't know why. I used to call it just reducing the quadratic. What we want to do is find a substitution so that we can get rid of this linear term, get rid of the second term. And so it's related to completing the square. We want to subtract off 5. Actually, this transformation, it's a graph transformation. We see it that way as well. But once we make that substitution, then the linear terms cancel out, and we're left with a difference of 2 squares. And this is wonderful because we can factor a difference of 2 squares. And again, we're using the 0 property. If the product of 2 numbers is 0, then one of the numbers has to be 0.
Or they can just solve.
Or you can,
2 squared for 4.
or we can move the 4 to the other side and solve like we did in the last slide. But I love this. The students don't often think that the reason we want a 0 here is because of the special property. If you multiply 2 numbers and get 0, then one of them has to be 0. It's like a statement in Converse. If you multiply by 0, the answer is 0. If you've multiplied and you get 0, then one of the numbers has to have been 0 to start with. And so we get our 2.
And where does the substitution come from? I'm very good on
Half
where
of
the
10.
x equals t minus 5 come from.
Half of 10x.
So you take
10x on top, half of
10x,
it. Yeah,
Okay, you take half of it, you know you're 5.
yeah.
You're substituting the variable t minus that half, that 5.
It's problem 7 actually, that is the precise statement for the precedent.
Okay, good. Yeah, so problem 7 I put there, that shows exactly how to do it.
So that's t minus half of b.
Minus B over 2A. But yeah, that's right, that's right.
Thank you. T minus b.
I think I might be able to show a visual
Let me use that.
one in a bit. Let's look at some of the other problems. Actually, I want to go back to this. In the factoring method, the way we're understanding this equation is that we're given the sum of two numbers, that's 10, and we're given the product of two numbers, that's 21. And those are the coefficients of the quadratic. But that makes it really simple. For number 2, find two numbers whose sum is 10 and whose product is 21. Well, the 10 and the 21 just drop in as coefficients. The product is the constant term. The linear term is negative the sum of the roots. So if we're given the sum and the product, we can just drop them in and come up with a quadratic equation that we can solve. Same thing here. We want a rectangle, so we have a length and a width. The product is 8, and the perimeter is 12, so the length plus the width is half the perimeter. We just drop it right there. And without doing much work at all, we can reduce this to solving a quadratic equation. So where did quadratics come from? Well, it could be an area and perimeter problem, which is very, very basic. Even the Babylonians must have been worried about how much area they have and how long it takes to walk around. Here's one, number 4. We're directly given the product and we're given the sum, so we can just drop those into the quadratic, and we have an equation. Number 5, I love this. Here's the equation. It has two solutions, find their sum. Well, it's standing there right in front of us. The sum of the roots is the negative of the linear term. So there's nothing to do. We don't even need to find the two solutions and then add them up. We can just find their sum by reading off the equation.
Go slow on that one.
Let's go through that again.
So again, I'm very visual, so when I see something, I'm trying to visualize it. Go back to the 5 though.
I think it helps
I didn't
actually.
hear it all.
See, are you here for the cubic equation? Come on down. Let's see. Let's give you a problem sheet. Here's a problem sheet, and here's one for you. And let's see, 2 more people. Here's one for you. We're just going over the first 8 problems, but you're here to the right time for a little history lesson. Okay, this is our evidence. Where are you guys coming from? Are you from Tempe? Yes. So we're just finishing going over the solutions for problems 1 through 8 on the problem sheet. But let's. Well, I think you had a question. Is where are those numbers coming from?
Isn't that just putting 4 in 5?
Yes, okay. So
Talk about
so
that.
that's why we're
Number 5.
I like terms.
Here's the way to think of it. We're looking for the two solutions. If we had those two numbers, let's call them A and B. Well, if we multiply this back out, we end up with the sum right here and the product. So if we want the sum of the two roots, we don't actually have to solve this equation. We can see that the sum of the two roots is right up here. We can just match the coefficients. So the sum of roots, we just have to equate coefficients. Plus 5 is negative A plus B. So we're looking for negative 5. without actually having to solve for the roots for the two numbers, we can do less and get the correct answer. So let's move on to number 6, I think. Can we move on? Number 6. Substitute x equals t minus 2 in this equation. Well, we're doing a graph transformation. And here's the original equation, x squared. Oh no, that's number 8. Plug this in. Well, that was depressing the quadratic, and that's similar to this solution for number 1. Make a substitution. Notice that here we have t minus 2, and that's exactly what we need to get rid of the 4x term, to get rid of the linear term. Who got an answer for number 7? I don't actually have that. Joycelyn, I saw you working on that.
No, it got too messy.
Got too messy? Did anyone have a form where it's not too messy? Welcome.
Am I too late or?
No.
Okay. Well, I got this plus or minus square root of b squared over 4a minus c, which is all wrong.
Sorry, that's just a substitution?
Yeah, substitute and then solve. So I got t.
Oh, okay. This is number 6. Do you have a substitution for number 7?
What do you want for 7?
Oh,
You want the 2?
For number 7,
Yeah,
just a substitution.
the substitution.
So if you
simplify.
you want t squared equal or t squared?
B squared equals to B squared minus 4AC
t squared equals b squared,
minus 4AC over 4A squared.
b squared minus 4ac,
Yeah, all over 4A squared.
4a squared. Okay. Okay, great. So you did a lot of extra work in there.
Yeah, substitute and then simplify and then.
But this makes sense. Look at what happens if you take the square root. We're going to get a square root of b squared minus 4ac over 2a, and of course there's plus or minus. So that substitution, where we use b over 2a, that's the axis of symmetry of the parabola, and shift it over. That's exactly what we need to give two solutions. One is a negative, one is positive, and they're centered around the origin. And the effect is really taking a parabola, shifting it so that the new axis of symmetry is the y-axis.
I don't know if you mentioned or not, but that term should look really familiar.
Yeah.
Yeah,
Right?
yes.
It should just pop out of you. Have you seen this term before? No, you haven't. Okay, where does this appear?
Which term?
Solution quadratic.
That t term.
Okay, so James, this is
Solution quadratic x equals
this is
negative b plus or minus.
can everyone see if I write here? What do you think? Negative b plus or minus the square root of b squared minus 4ac over 2a. Does that look familiar?
Mm-hmm.
Okay. So notice that the negative b over 2a, that's right here. And when we make the substitution, we end up with the rest of it. Okay. So let's move on. Let's have a history lesson. Okay, the history of the quadratic formula. The quadratic formula was actually solved solved by the Babylonians. They had a very different understanding of number. They didn't believe in zero or negative numbers. So their solution was inconvenient to say the least. Euclid, here's a picture of Euclid, was able to solve quadratic formulas using geometric methods with a straight edge and compass construction. Okay. Move to the early 600s. The Indian mathematicians actually were the first ones to introduce negative numbers and zero. And so Brahmagupta, a famous Indian mathematician, was able to expand the original Babylonian solution method to include quadratics where coefficients were negative. Of course, they didn't have our wonderful system of algebraic notation, so it was more difficult. Around 800, now I'll try to say it, Al-Khwarizmi, he was an Arab mathematician. He didn't have the understanding of negative numbers or zero, even though Brahmagupta had, and the Indian mathematicians had brought that in earlier. Al-Khwarizmi had to classify quadratics in a very painstaking manner. You could have a square and the root equaling a number, or a square and a number being a root, or the root and a number being the square. Since we have a nicer notation and we allow negative numbers, we're tempted just to throw everything over on one side of the equation and put a zero there. But Brahmagupta would not deal with negative numbers. So he had to separate quadratics into all the different cases. There's some further cases without the quadratic term, and solve them separately. And he understood them as very different things.
And if you go back and read his work, what makes it even more interesting is he didn't use variables.
He didn't use variables. The use of this modern notation wasn't until Witte,
1590.
What did he use? A visual.
He'd spell it out in words. He would say a number, the square of a number plus 10 times the number is 39, just in words. And it wasn't for many centuries until this notation started to develop. Imagine trying to solve each of these equations, writing on every step as a paragraph. Not something that we want to do. But the notation gives a lot of efficiency in solving these problems. Al-Khwarizmi is known as the inventor of algebra. He developed all sorts of algebraic methods and treated these equations with an unknown. Earlier, everything was a specific type of problem. And later on, Savasurna actually published the first complete solution of the quadratic equation in a book in Europe. Okay, there's Savasurna sort of reached out, and Al-Khwarizmi. His name is an Arabic name. It's become a word in the English language. Do you know what the word is? Algorithm. It's an algorithm. He presented a step-by-step procedure to solve problems. That's what we call an algorithm, and that comes from Al-Khwarizmi's name. That changed over time.
Wasn't there another percentage who was talking about?
No, that one, algebra is also Arabic, but it's the actual word al-jabr, which means mending or solution. Actually, both doctors are called algebristas. He also
But it did come from him. It did come from him. It's a fragment of the title.
Right.
But yeah, that's right.
I was thinking this is name.
Okay. Let's talk about the cubic. This class is about the cubic. Cubic equations actually could go back to Euclid. The ancient Greeks were interested in trisecting an angle. If you given an angle, the goal was to divide it into 3 equal parts with a straight edge and compass construction. If we, so given an angle 3 theta, the goal was to construct theta. In modern notation, this is equivalent to if you're given the cosine of 3 theta, construct the cosine of theta. And the trigonometric identity, cosine of 3 theta is 4 cosine cubed theta minus 3 cosine theta. That's actually a cubic formula. We're given this number, and we'd like to solve for cosine of theta. If we replace cosine by x, cosine cubed by x cubed, we're given a number, let's call it a. Then trisecting an angle is equivalent to solving the cubic equation, and the Greeks could not do that with a straight edge compass construction. Omar Khayyam, pictured on the left, he considered the cubic formula, and things start to happen in the late 1400s, early 1500s. Luca Pacioli discussed solving a quartic. He wasn't able to do it, but he really focused the discussion on solving polynomial equations. Rumor has it that Luca Pacioli visited the University of Bologna in 1501, 1502, and met with Scipione del Ferro. Del Ferro actually managed to solve the cubic equation. He solved equations of the form x cubed plus mx equals n, and he kept it to himself. This was a secret. Back then, mathematicians would solve a problem and then hold that as a secret weapon because they would have to challenge each other in contests. And if you can solve an equation that other people couldn't, then when you issued a challenge, you can give them a problem that they can't solve but you can, and you'll win the contest. Nowadays, we want to publish first and gain claim to the discovery. But back then, it was a secret weapon because to gain a position as a professor, you had to defeat your opponents in a mathematical tournament. Del Ferro's solution involved the basic arithmetical operations and extracting roots. He used square roots and cube roots, and that was sufficient. He kept it secret until his deathbed. In 1526, he revealed it to his student Fiore. Fiore was not a very powerful mathematician. In the end, he had solved the cubic equation, and that was about it. And he got a lot of mileage out of it. He went around boasting that he could solve the cubic equation, and he could. Sometimes when you know that something is possible, then you can do it too. Niccolo Fontana, who's known as the stutterer, Tartaglia, he heard that someone had solved the cubic equation, and he actually independently then solved it on his own, and made it known that he could solve cubic equations of this form: the cube plus the square equals a number. Those are slightly different. It's not immediately obvious that if you can solve one form, then you can solve the other form. So what happened? Del Ferro's student, Fiore, was very upset and challenged Tartaglia to a duel. By the way, here's Tartaglia, the only known remaining photo of Tartaglia. This is a woodcut you can find on the web. So Del Ferro's student Fiore challenged Tartaglia to a mathematical duel. And, today there's a math contest for all students. I think an 8th grade contest and a 12th grade contest. So maybe this is kind of a flavor for what it was like being a mathematician in medieval Italy. You had to fight these mathematical battles to defend your position. So Fiore challenged Tartaglia to a duel, 30 problems. Each of them would present the other one with 30 problems to solve, and they would have about a month, maybe 2 months to solve them. Tartaglia was actually a very well-rounded mathematician and scientist, and he laid down 30 questions from all areas of mathematics and science for Fiori. Fiori only knew how to solve a specific kind of cubic problem and wrote down 30 cubic problems for Tartaglia to solve. And guess what happened? Tartaglia, who had independently solved a different form of the cubic, figured out how to solve the 30 problems that Fiori presented to him, solved every one of them in a very short time. But Fiori, who had only solved the cubic equation, he didn't solve a single problem laid down by Tartaglia. And after this crushing defeat, Fiori pretty much faded away into history and was not heard from again. So now comes Cardano. Here's a nice picture. Here's another picture of Cardano. Cardano was writing a textbook at the time, and he heard rumors that Tartaglia had solved the cubic. So he sought Tartaglia out and wined and dined him and had him reveal the secret method for solving the cubic equation. And he swore himself to secrecy. He says, I won't tell a soul. Yeah, right. Next thing that happened, Cardano was working with a student, Ferrari. Cardano revealed the solution and sent Ferrari off researching the quartic. Ferrari was actually quite a bright guy. He managed to find a solution for the quartic equation by reducing it to a related cubic equation. So with Ferrari's method in hand and Tartaglia's method, that Cardano actually discovered that Del Ferro had previously solved the cubic. Cardano published both solutions, giving them credit. Here's Tartaglia's cubic solution, and here's Ferrari's quartic solution. Published them in his book, Ars Magna. And of course, Tartaglia was furious, but what could he do? It was already in print. And even though he had discovered it, and Cardano credited it to Tartaglia, now we know it as Cardano's method. So things have changed. Now we know that we have to publish. So the last story with the cubic, a few years later, Tartaglia was offered a professorship. They said, Tartaglia will hire you as a math professor, provided that you can defeat Ferrari in a mathematical battle in a contest. And I think Tartaglia had remembered back from defeating Fiori how easy that was. Fiori was the student of Del Ferro. Said, who is this guy Ferrari? That's just Cardano's student. I could take him on with my hands tied behind my back. Didn't do much to prepare. Ferrari was actually quite a formidable foe. And Tartaglia was crushed in this contest. Didn't get the professorship and was bitter for the rest of his life for this betrayal. Cardano had betrayed his trust, and he was not a happy man. So that's the first talk. Let's work on the rest of the problems. Okay, I'd like you to pair up this time, and we're going to have, let's see, we'll have about 20 minutes to work on the rest of the problems. I'd like you to especially look at problems 21 and 22. Make sure that you've read through the statement of every problem, see what you can solve. I'd like you to work in pairs. I want to see everyone working with a buddy and share your solutions. And after 20, 25 minutes, we'll come in and finish up the class with a talk about the cubic formula. You have to okay. You did the cubic solution. You did? Okay. That would be helpful. I'd love to hear what you think about these problems, especially in relation Okay.
I was thinking actually, Alex.
Can you work on board? And
Yeah.
maybe the three of you can work on it.
I want
Well, this is the first time we've done it, so I'll get it. I'm looking at it.
It's really nice to see some.
So this one you should try to get to. Have you done fractions before? Okay, so you should try to. And then this one's good too.
which you can use, yeah.
So I'll just get started by it. How old are you? Grade year? So have you ever done probability or statistics like that? That's like, I'll give you one. So this one you might understand.
I love those.
Those are cool. What you might want to do right now, if you wanted to, you can just go next door and go to there's different tables. You can go over on the first, like, you can see the whole entire lecture really well.
And that's good practice.
So you know
We are right here.
Some of you numbers is five.
So these are all lectures on our class. There's in this room and all of these rooms, there's not very many people over there right now. So go into this room especially, there's something called zones, and you get to build them up and you get to make this shapes and think about it. There's that, and then that way you don't have to just be part of it. Have fun. Should you ask anyone about that?
Yeah.
It's just like for
No, that's not. That's what they say. Right. So it is the sum of those, right?
Well, but they really, but I find that they really respond to as soon as you start making what I find interesting is that even if it's also deep.
So you have to get an idea.
Yeah, so if I have my unknown number, I know that my number is 35.
So that's what you get if you do A plus B squared plus A times
Right.
But then if we want to find out what A squared plus B squared is instead. So A and B are unknown.
Okay. Thank you.
No, you can. That's right. So what did you say? You can have a 5 person. So then you probably.
So once we're isolating A,
So a squared plus b squared.
that is a change B squared.
Yeah, a is
That's easier.
So a is
So this is, so now,
so we need to square root of what's that? So we need to somehow get a squared to
On
b
the other
squared.
side.
A is
This is kind of mathematics.
Oh, no, I agree. Square root.
And then. This is a square root of
So that's 9 and 10 all over. It should be a plus 2, subject to 4, so we're gonna have the derivation. So I just
So this is some way to get, so we need some formula in all these. So then you can remove one of these two numbers that we know. That's going to give us an a squared. So if we did just a plus b squared.
we've got the sum is 5. So for B6.
And for you, can you generalize one?
No, just up to I.
So the really thing is,
Possibly not.
I guess technically 12 and 13.
And we multiply them. Right, that's almost the kind of conclusion of the process.
Let's simplify what we have inside these parentheses. So then that's going to be x.
so it's also a b
This
plus
one.
itself this equation.
This one we could write
Yeah,
as
X plus 1.
X squared, we have plus 5, right?
Minus. Because
Because
you remember what we did before?
Plus 3.
So we know that
If you
x minus a, x
Except
minus c is
if
this.
you square this one, you will have.
So we're just replacing x plus 1.
Yeah.
And we're going to put it into
And then that's a square plus 2. Okay, so then this is
So you can also
then
see
start
x.
simplifying.
So you can take this, replace each x by x plus 1.
And then that's this. So you get this one, then you buy this one, you get this one.
Yeah.
And then that.
I think that was the end of it.
This is square, and this is square. Okay, that's it. Okay. So everyone will agree with that, same. And then this one now, then we will get the square of this one. Okay, for your work, just get this one. Just get this one.
So that's also
This is not big, this
when
one's not big. If everything's
in the same part when we were shifting the fraction.
So
We
we're
went
really,
shifting the x1.
so then we need another fraction. Since we think two pairs.
Right.
Combine this into
So
this
this
one.
would be root.
So that
So a and b.
or divided by one.
And you get more than that.
That's 25 over 4.
Bandages on it.
Some
Hands just don't fit.
So in other words, this one, you don't know whether to extract the square. How can you extract the
But you
square?
end up with
Because the square of the number, this one is saying plus 1.
Right, right. That was quite a facility. So that was like.
Hello?
It's the same to it.
Yeah. Okay. I think that they both do balance.
You got the 2 square root
Well, I guess.
you got this, you got
Well, I just, if one was just going to. Well, yeah, I mean, so one could, in principle, one could solve the square and therefore solve it doesn't seem. So you have to solve it.
using some.
Yeah. Okay, so you want because it works out.
Yes, yes.
So you were able to reduce it to a cubic, and then you were left with a
Rational, yes. What? Yeah, so nothing practice.
So we know what A plus B.
Yeah.
So if you square A plus B,
Yeah, it's because it's all.
A squared plus B squared. So there you have A squared and B squared. And a little bit of extra. But we know what this, so we know A plus B is 5.
Yeah.
So this is 25.
We're going to work for 5 more minutes, and then we'll come up for another coffee.
Yeah.
Okay, so that's not the equation.
I should be in the wine, but I got the things.
You expand this as a quadratic. So on this side here, there's 5x squared.
And so we know what AB is.
So should we do the same A squared plus B squared?
So 17 is some similar way to
No, I don't know about one.
So we got that.
And I think you have 47. So we have to think about
What's on this side?
You don't have 15 21?
no, 15 years ago.
15 years.
Yeah, but now it's 30 years ago. So I know.
Right.
And we know AB was.
But then like,
What's the
And so that's not.
No,
Right.
so you've got the 25 here. It's 25, you just run it from there. I'm gonna put it up here because, now it's the first one. I got 24 A plus B squared. Squared, I would say,
Okay, 2 more minutes. If you haven't looked at problems 21 and 22, take a look at those now.
So this is one number.
So I can actually do this. Oh, that for the y.
Yeah, well, so now we have this one, we have this one. Yeah.
And by this now.
So you put that on the end.
Y over here.
X,
And then you combine.
so this is y. So this x will be equal to 1. So this is going to be 1. So that's not
Yeah, you're right. That is in this case.
oh, let's see.
One has really nice.
Y.
Yeah.
But then the other two solutions, you need to some but one of them works out.
But I mean, is there some?
But there is no shortcut. You need a cubic for a.
If you take A plus B root 3, it's you can.
Yeah, this is.
And then the sum of
That's how we can make what's
This is that.
for what?
That's the word problem. Yes.
And then put different vacuum here, so we got stuff here. I still cannot solve it.
I'd like everyone's attention up here. We're going to continue with the process. So put away your problems for now. Take out some note paper if you like. Keep the problem sheet handy because we're going to look through some solutions of all of the problems. So Randy, put the problems away. We're going to come back up. We're going to finish up. We have 20 minutes to wrap everything up. The problem sheet has much too many problems to finish in one session. And so when Lorna, let's have your attention up here. And we're going to go through some of these. I'll give you a lot of feedback on some of these. You may want to take the problem sheet home and continue to work on it. It's full of a lot of rich problems. But our goal, if you turn the problem sheet over, you'll see that the goal is to solve a couple of cubics. There's some target cubics at the top of the page. And so what we'll talk about, at the end, we'll see solutions for a couple of those cubics, and we'll get a general formula. So first, there's sort of some hidden knowledge that you have to know to find the most beautiful, efficient way to solve these. And it's called symmetric polynomials. In fact, they're elementary symmetric polynomials. If we have two variables, a and b, then a function is symmetric with respect to a and b if when we switch them, we'll get the same function. If we have three variables, a, b, and c, a symmetric function is a function where if you switch any pair of a, b, and c, you'll get the same function. We're specifically looking at polynomials. So a symmetric polynomial is where if you switch any two of the variables, you'll get the same polynomial. These ones, S1 and S2, and for three variables, S1, S2, and S3, those have special status. Those are called the elementary symmetric polynomials. And they show up naturally from quadratics and cubics. If we have a quadratic whose roots are a and b, then the sum of the variables shows up as the negative of the linear coefficient. The product, that's the other elementary symmetric polynomial, shows up as the constant term. With three variables, if we have a cubic whose roots are a, b, and c, then the sum of the roots shows up as the coefficient of x squared, but with a minus sign. The sum of the products taken two at a time, that's the second elementary symmetric polynomial, shows up as the coefficient of the linear term. And then the product of the roots is the negative of the constant term. So these elementary polynomials have special status, which will let us solve 9 and 10. Some of you noticed that 9 and 10 were special cases of problems 21 and 22. For 9 and 10, the direct solution is to just find the solutions. For number 9, the sum of two numbers is 5, and the product is 3. So we're given the sum of the product. That means that we're looking for solutions of this quadratic equation. If we're given the sum of the product, we can just drop those into the coefficients of a quadratic equation, and we can solve the quadratic. The two solutions are not very beautiful, but if we find the solutions and we square them, then we can get the correct answer. But there's a nicer way to do that because of an identity in problem 21. So Stephen, I think I saw you writing it out.
You just take a plus b squared.
A plus b squared.
A squared plus 2ab
A squared plus 2ab plus b squared. We can rearrange the terms. A squared plus b squared, the sum of the squares, which we find over here, that's the square of the sum, which we find over here, minus twice the product of the numbers. So notice this is s1 squared minus 2s2. Here's a symmetric polynomial. If we switch a and b, we'll get the same polynomial. We can take any symmetric polynomial and express it in terms of the elementary symmetric polynomials, s1 and s2. So in this case, this is s1, this is s2. So the sum of the squares is 5 squared minus 2 times 3, 25 minus 6, gives us an answer of 19, and we don't even have to know the two solutions. Nice. For 22, did someone, Joycelyn, I think you had you were working out on a cubed plus b cubed.
Oh, yeah.
Well, do you have a formula in I could write out?
A cubed plus b cubed
A cubed plus b cubed
equals the sum on A plus B cubed
A plus B cubed
minus
minus
3AB
3AB
times 1B A plus B.
A plus B. Great. Notice that this is S1 cubed minus 3S2 times S1. So here's a symmetric polynomial. If we switch the variables, we get the same polynomial. And we can express it in terms of the elementary symmetric polynomials. And so we can use this to solve number 10. We can solve 10 by first finding the two numbers, cubing them, and then adding them together. But we could do this. We're given that the sum is 10, so 10 cubed, and this is 10. And the product is 13. So the answer that we're seeking is 1,000 minus 390, and we get 610. Who worked this out by finding the two numbers, cubing them, and adding them together? That's a great way to do it. If you have a student who solves it this way, they're building their strength. They'll become more mathematically powerful, and then this will be a joy to see. But if you don't have the practice working through the computation, then it doesn't have the special joy from doing it. Let's focus in on the sum of the cubes. There's a couple of things that I want to show you with this. One is that we're moving towards the cubic formula. Because notice, we have A plus B cubed and A plus B. If A plus B is the unknown, then we already have a cubic equation hidden inside of this identity. And we're going to come back to that. But I wanted to focus on this because this gives nice solutions for 23 and 24. Did anybody have a chance to work on 23 and 24? Would you like to see a nice solution? Would you like to see a nice solution? Okay. You know that if you could use brute force, you could just multiply everything out, collect like terms. You're going to get a cubic equation because this is degree 3, this is degree 3, and this is degree 3. So there's at most 3 solutions. At most 3 solutions. But it has a special form. Did you notice that x minus 3 plus 5x plus 10 equals 6x plus 7? You notice that? So here's the key. Number 23 has the form a cubed plus b cubed equals a plus b cubed. If this is a and this is b, this is a plus b. There's the identity. We know that a cubed plus b cubed is equal to a plus b cubed minus something. So with this given and this identity, that means that minus 3ab a plus b must equal 0. It's already in factored form. This means minus 3x minus 3, 5x plus 10. And then a plus b is the 6x plus 7 is 0. Which means that we can just read off the solutions. Here's the 3 solutions without doing any work. This identity gives you a lot of mathematical power. Okay. I'm tempted to just leave this with you and see if you can make use of this identity to find an equation for number 24. But it works out very, very nicely. So there's some power there. Let's look at 12 and 13. Okay. I call these hidden quadratics. James, I saw that you reduced those to a cubic, but they're actually quadratics. And here's one of the key ideas of the cubic formula, that you can take an equation, a system of equations like this, and you can reduce it to a cubic. You can also reduce it to a quadratic. And that's the connection that will let you reduce a cubic to a quadratic. So let's see how that works. So we're given the sum of the cubes equals 20, and the product of the two numbers is -2. Let me write the second equation in a slightly different form. U cubed times B cubed equals -8. Notice that I have the sum of two cubes and the product of two cubes. That means I have something like this. I have the sum of two numbers and I have the product of two numbers. And if I'm given the sum and the product, I'm really given a quadratic equation. So there's a hidden quadratic equation in here. This says that x squared minus 20x minus 8 equals 0. I'll drop in the sum and drop in the product, of course, make this one negative. I actually have a quadratic equation in there. And if I can solve for x, then I can solve for u and for v. Let's go through and do that. I think we have to use the quadratic formula here. X is 20 plus or minus b squared minus 4 times 8, 4ac, or 2.
And minus a.
Did I?
Time minus a.
Minus a.
Minus 8.
Where is it?
Minus 8.
Sign.
Oh, so this should be a minus 8. Thanks. Okay. So I left it in this form because we can actually reduce this. 20 over 2 is 10, plus or minus. Here, I can get rid of a 4. Isn't this 10 squared? And I can get rid of this 4. So it's actually the square root of 108. So this means that u cubed is 10 plus root 108, and v cubed could be the other one, 10 minus root 108. Okay. And as a result, u is the cube root of 10 plus 108, root 108, and v is the cube root of this other number, 10 minus root 108. It's a hidden quadratic. Just by cubing the second equation, I can drop it into a quadratic, solve it. That gives me the cube of the solution, so I just need to take the cube root. Let's look at let's look at 13 another way. Okay. For 13, there's another way to turn this into a hidden quadratic. Let's solve for b. The second equation lets us solve for b. b is negative 5 over a. So if I plug it into if I substitute that into the first equation, I'll have a cubed minus negative 5 over a cubed equals 4. That's a cubed 125, so it's a plus 125 over a cubed equals 4. I can multiply both sides by a cubed, end up with a to the 6th minus 4a cubed plus 125 equals 0. And I've reduced this to a 6th degree equation. but it's a hidden quadratic. This is a cubed squared minus 4a cubed plus 125 equals 0. Notice that this 4 shows up right there. That's the sum of two roots. And this negative 5 shows up there. That's the product of two roots, but we have to cube it. So it's a hidden quadratic. That means that a cubed is, well, here's a quadratic in a cubed, not a quadratic in a. So a cubed is, let's use the quadratic formula again. 4 plus or minus the square root of 4 squared minus 4ac all over 2. I'm not going to multiply this out because I can first reduce. There's a 2 here. I think I have room up here. A cubed is 2 plus, this is going to be 4 minus 125, negative 121. And
You lost the minus signs.
did I lose a minus sign? Plus or minus?
No, that's a minus 4?
This one, if I factor out its
No, at the beginning. Oh, sorry, minus B.
No,
Yes,
it's not.
you're right, sorry.
so
Yeah, no,
it's
you're right,
actually
you're right.
more.
Thanks,
Okay,
sorry.
It's one of those times.
I just got confused.
I
because
just
I'm
did
doing the mental thing, yeah.
So I can actually solve for a. A cubed is 2 plus or minus root negative 121. Let's make a the positive, and then b cubed. Well, a cubed minus b cubed is 4, so it's going to be a little bit different. B cubed will be negative 2 plus root negative 1. Gives a new cubic, the sum of whose roots is 0. And that adds enough symmetry that we're going to build a cubic formula from there. So here's, we're going to use cubic of interest number 1. That's actually the answer to number 18. Let's look at this. What we're going to do is match this cubic up with this identity. And notice that this identity is a cubic in U plus B. So if we can match up the coefficients so that 6 and negative 3uv are the same, and 20 and u cubed plus v cubed are the same, then solving for u and v, we'd actually have a solution by adding them together. Should we go through that again? We're trying to match up the given cubic and that identity that the sum of the cubes is the cube of the sum minus something. Notice that this is already, it has the form of a cubic. If we can match up the coefficients and 6 with negative 3uv, then it would be done. But we've actually done the work. This is problem number 12. This is problem number 12, and we saw that one solution is cube root of 10 plus root 1 of 8, and the other is the cube root of 10 minus root 1 of 8. So here's one solution. We've actually done the work to get the solution. Here's another, the other one of interest. Gives this solution. We've actually done the work right up here. By making a substitution of x equals a minus b up here, with ab is negative 5, this reduces down to problem number 13. This reduces to exactly what we have here. And so what this is here's that shift. Actually, this one is a strange cubic. Here's the picture. It crosses the x-axis 3 times. So there's actually 3 real roots. But Cardano's method gives this. It's the sum of cube roots of complex numbers. And somehow that actually equals 4. And so this was a problem that really got Bombelli to understand complex numbers better. And here's the